Physicist, what is one piece of physics knowledge that everyone should know? Story 1. One thing more people should understand is that not all radiation is the same, because the word radiation immediately makes people think of nuclear accidents or cancer, when in physics it really just means energy traveling through space in the form of waves or particles. 5G signals are in the radio frequency part of the electromagnetic spectrum, which is non-ionizing radiation, meaning the waves simply do not carry enough energy to break chemical bonds or damage DNA the way ionizing radiation like X-rays, gamma rays, or certain ultraviolet wavelengths can. That energy difference matters a lot. Ionizing radiation can physically knock electrons off atoms and molecules, which is why it can damage cells and potentially lead to cancer. But radio waves, including those used for Wi-Fi, Bluetooth, cell phones, and 5G, are far lower energy and don't have the physics required to do that kind of damage. At most, very strong radio frequency exposure can produce heating effects, which is the same basic principle behind something like a microwave oven. But the power levels used in communication systems are nowhere near that level and are regulated specifically to stay well below harmful thresholds. So the idea that 5G causes cancer doesn't really fit with how electromagnetic radiation actually works. It's one of those cases where a scientific term gets associated with fear, and once people hear radiation, they stop distinguishing between completely different parts of the spectrum that behave in fundamentally different ways. Story 2. That a light year is not a measure of time, even though the word year makes it sound like it is. A light year is a distance. Specifically, it's the distance light travels in 1 year through a vacuum, which ends up being about 9.46 trillion kilometers. And the reason astronomers use it is because space is so absurdly huge that normal units stop being practical very quickly. Saying a star is 40 trillion kilometers away is technically correct, but it's hard to intuitively understand numbers that large, while saying it's about 4 light years away immediately tells you something more meaningful. It also creates one of the strangest realizations in physics. Because light takes time to travel, looking farther into space also means looking farther into the past. If a star is 100 light years away, the light reaching your eyes tonight actually left that star 100 years ago. You are literally seeing it as it existed in the past, not as it is right now. And once distances get large enough, like galaxies millions or billions of light years away, astronomy starts turning into a form of time travel observation where telescopes become tools for looking backward through cosmic history. So the term light year isn't describing how long something lasts, it's describing how unimaginably far away things are, using the fastest thing in the universe as the measuring stick. Story 3. The greenhouse effect. It's both incredibly important and surprisingly misunderstood, mostly because the name itself gives people the wrong mental image of how it actually works. A literal greenhouse mainly stays warm because it physically blocks convection, meaning the warm air inside can't easily escape and mix with cooler outside air, so the heat gets trapped. But Earth's atmosphere doesn't work like a giant sheet of glass sitting over the planet. The real mechanism is about radiation. In physics, there are 3 main ways heat moves around: conduction, convection, and radiation. Conduction is heat transfer through direct contact, convection is heat carried by moving fluids like air or water, and radiation is heat transferred through electromagnetic waves, like sunlight or infrared radiation. Sunlight reaches Earth mostly as visible light, which passes through the atmosphere relatively easily and warms the surface. Then, the Earth re-radiates that energy back upward as infrared radiation. And this is where greenhouse gases become important, because molecules like carbon dioxide, methane, and water vapor absorb and re-emit infrared wavelengths very effectively. So instead of all that heat escaping directly into space, part of it gets redirected back toward the surface and lower atmosphere, effectively slowing down the planet's cooling. That's the actual greenhouse effect. Not heat being physically trapped like in a sealed box, but the atmosphere altering how efficiently Earth radiates energy away into space. And once you understand that, climate science starts making a lot more sense, because the entire issue comes down to Earth's energy balance, how much energy comes in versus how much escapes back out. Story 4. A lot of people picture a black hole as this cosmic vacuum cleaner that suddenly starts pulling in everything nearby the moment a star collapses. But that's not actually how gravity works at all. If the sun were magically replaced with a black hole of the exact same mass, the Earth wouldn't suddenly get sucked in. It would keep orbiting almost exactly the same way it does now. That's because gravity depends on mass and distance, not on whether the object is a normal star or a black hole. From far enough away, a black hole with the sun's mass would exert the same gravitational pull as the sun itself. The only major difference is that there'd be no sunlight anymore, which would obviously become a huge problem for us very quickly. But orbitally, Earth would continue moving normally. The reason black holes have this reputation is because if you get too close, the gravity becomes extreme enough that escape becomes impossible once you cross the event horizon. But outside that region, they obey the same gravitational rules as anything else. In fact, if our sun actually became a black hole naturally, which it can't because it's not massive enough, the resulting black hole would only be a few kilometers across while still containing the same mass as the entire sun. So the dramatic everything nearby gets instantly consumed image mostly comes from science fiction exaggerating what black holes actually do. They're terrifying, but in a much more precise and physics-based way than the giant cosmic vacuum cleaner people imagine. Story 5. The frustrating thing about quantum mechanics is that it's genuinely weird enough on its own that people feel the need to pile even more nonsense on top of it. And somewhere along the way, quantum became a magic word people use to justify basically anything they want to sound scientific. You'll hear claims about manifesting reality, speaking intentions into the universe, manipulating human energy fields, consciousness altering the cosmos, or quantum entanglement allowing faster-than-light communication. And almost none of that has anything to do with actual quantum physics. Real quantum mechanics is strange, but it's strange in a very mathematically precise way. Particles exist in probabilistic states. Measurements affect systems. Entangled particles show correlated behavior across distance. And quantum fields underlie matter itself. But none of that means human thoughts can rewrite reality, or that your mindset can directly alter the universe through hidden quantum forces. A big source of confusion comes from words like observer in quantum experiments, because people interpret that as human consciousness literally creating reality, when in physics, an observation just means an interaction that transfers information, like a detector measuring a particle. And entanglement is another huge one. Yes, entangled particles influence each other's measurable states instantly across distance, which Einstein famously hated, but it still cannot be used to send usable information faster than light, because the outcomes are fundamentally random until compared through normal communication afterward. The actual reality of quantum physics is already bizarre enough without turning it into space mysticism. And honestly, the real science is way more interesting than the pseudoscientific version people try to sell. Story 6. The weird thing about light is that we interact with it constantly every second of our lives. Yet most people never really stop to think about what it actually is. And when you do, it gets strange very quickly. A lot of people intuitively think of light as just brightness or something objects produce. But physically, light is an electromagnetic wave, meaning it's made of oscillating electric and magnetic fields traveling through space. And unlike sound, it doesn't need air or any medium to move. It can travel through a vacuum, which is why sunlight can cross 150 million kilometers of empty space to reach Earth. Then it gets even stranger because light also behaves like particles. Depending on the experiment, it can act like a wave spreading out through space, or like discrete packets of energy called photons. And both descriptions are necessary because neither one alone fully explains its behavior. That's the whole wave-particle duality thing people hear about, and it isn't just theory, it's experimentally verified over and over. Color is another thing people misunderstand. Objects don't have color in the way we instinctively think. What we perceive as color is just different wavelengths of light interacting with our eyes and brain. A red apple looks red because its surface absorbs most wavelengths and reflects the red wavelengths back toward you. And perhaps the strangest part is that when you look around, you are never seeing things as they are right now. Light takes time to travel. It's tiny at everyday distances, but it means you always see everything slightly in the past. And on cosmic scales, telescopes become literal time machines looking billions of years backward through the universe. So light ends up being way more than stuff that lets us see. It's one of the most fundamental things in physics, tied to electromagnetism, relativity, quantum mechanics, and the structure of reality itself. Story 7. The most important thing people misunderstand about physics is that scientific models are not truth, in some absolute sense. They're tools that describe reality as accurately as possible, based on the evidence we currently have. And sometimes those tools work incredibly well even while we already know they're incomplete. Our current understanding of the universe is full of examples like that. General relativity predicts gravity and large-scale cosmic behavior with absurd precision, while quantum mechanics explains the subatomic world so accurately that modern electronics literally depend on it. And yet those two frameworks fundamentally do not fit together cleanly. They both work, they both match experiments, but at the deepest levels they conflict. Then you add things like dark matter and dark energy, which together seem to make up most of the universe, except we still don't actually know what either of them are. We include them because without them, the equations stop matching observations. That doesn't mean the models are useless or fake. Far from it. Physics works astonishingly well. The GPS in your phone literally has to account for relativity to function properly. Quantum mechanics gave us semiconductors, lasers, and modern computing. But science is always provisional. A model survives because it predicts reality better than competing ideas, not because it's considered eternally perfect. And sometimes there may not even be a simple true picture underneath everything, in the way humans intuitively want there to be. So a huge part of physics is accepting that our understanding of the universe is probably incomplete, possibly deeply incomplete in places, while still being useful enough to build working technology and make accurate predictions, which is honestly a much stranger idea than most people realize. Story 8. A thing more people should understand, not just in physics but in science generally, is that science almost never deals in absolute proof the way people imagine. And confusing evidence with proof is probably one of the biggest reasons scientific discussions go off the rails online. In mathematics, you can prove something within a logical system. But in science, you're dealing with the real universe, which means conclusions are built from evidence, observation, prediction, and repeated testing, not from absolute certainty. So when scientists say there's overwhelming evidence for something, like evolution, climate change, or relativity, that doesn't mean blind faith or just a theory. It means the available evidence consistently points in that direction so strongly that alternative explanations fail to account for the observations nearly as well. And that distinction matters because people often treat anything short of 100% certainty as if it means we know nothing, which is not how rational reasoning works. You don't need absolute proof to make reasonable conclusions. You operate on probabilities constantly in everyday life already. You trust planes will fly, medicine will work, and bridges won't collapse, not because you personally proved every principle behind them, but because there's an enormous body of evidence supporting those systems. At the same time, science also requires remaining open to revision if new evidence appears, which is another part people struggle with. Changing a conclusion in light of better evidence is not a weakness. It's literally the mechanism that makes science work. So the goal isn't blind certainty or blind skepticism. It's being able to weigh evidence honestly, accept the best supported explanation available, while still understanding that no scientific model is beyond questioning if stronger evidence eventually appears. Story 9. A lot of people hear the word scientific theory and think it means guess or speculation, when in science it basically means almost the opposite. In everyday conversation, people say things like, "I have a theory," when they really mean a hunch. But scientifically, a theory is a framework that explains observations, survives repeated testing, makes accurate predictions, and holds together under scrutiny across a huge amount of evidence. That's why things like the theory of evolution, germ theory, or quantum theory are called theories, not because scientists are unsure whether they're real, but because they're large explanatory systems describing how parts of reality work. And quantum mechanics is actually a perfect example of this distinction. We still don't fully understand why reality behaves quantum mechanically at the deepest interpretive level, and physicists still debate what mathematics ultimately means philosophically. But the predictions themselves are unbelievably accurate. Modern electronics, lasers, semiconductors, MRI machines, and huge parts of modern technology work specifically because quantum mechanics predicts outcomes correctly. So when people say it's just a theory, they're accidentally downgrading one of the strongest categories science actually has. A scientific theory is what you end up with after an idea survives massive amounts of evidence and testing, not before. And that's something a lot of people miss because the scientific meaning of the word and the everyday meaning are almost completely different. Story 10, Newton's third law of motion is one of those physics ideas people memorize in school, without ever really internalizing how weirdly universal it is. Because once you start noticing it, you realize basically nothing can interact without forces coming in pairs. People usually think of it in dramatic terms, like rockets blasting off or guns recoiling, but it's happening constantly in completely ordinary situations. Right now, while you're sitting still, gravity is pulling you downward toward Earth, but at the exact same time, your chair is pushing upward on you with an equal opposing force. If it didn't, you'd accelerate straight through it. And the important thing is that these aren't one force canceling itself out. They're two separate forces acting on different objects. You push on the chair pushes on you, the Earth pulls on you gravitationally, and you also pull gravitationally on the Earth, just with an effect so tiny compared to Earth's mass that you never notice it. That's the part people often miss. Forces always come in interactions. There's no such thing as a lone, isolated force existing by itself. Even walking works because of this. You push backward against the ground with your foot, and the ground pushes you forward. Without that reaction force, movement wouldn't happen at all. And once you really understand that, physics starts feeling less like objects doing things independently and more like a constant exchange of interactions between everything touching, pulling, colliding, or exerting influence on everything else. Story 11. Newton's third law of motion is one of those physics ideas people memorize in school without ever really internalizing how weirdly universal it is. Because once you start noticing it, you realize basically nothing can interact without forces coming in pairs. People usually think of it in dramatic terms, like rockets blasting off or guns recoiling, but it's happening constantly in completely ordinary situations. Right now, while you're sitting still, gravity is pulling you downward toward Earth, but at the exact same time, your chair is pushing upward on you with an equal opposing force. If it didn't, you'd accelerate straight through it. And the important thing is that these aren't one force canceling itself out. They're two separate forces acting on different objects. You push on the chair pushes on you. The Earth pulls on you gravitationally, and you also pull gravitationally on the Earth, just with an effect so tiny compared to Earth's mass that you never notice it. That's the part people often miss. Forces always come in interactions. There's no such thing as a lone, isolated force existing by itself. Even walking works because of this. You push backward against the ground with your foot, and the ground pushes you forward. Without that reaction force, movement wouldn't happen at all. And once you really understand that, physics starts feeling less like objects doing things independently, and more like a constant exchange of interactions between everything touching, pulling, colliding, or exerting influence on everything else. Story 12. One of the strangest things in physics, and something that completely breaks a lot of people's intuition, is that conservation of energy is not actually a universal rule in the way most of us are taught in school. People learn energy cannot be created or destroyed, almost like it's a sacred law of reality itself. But in modern physics, especially cosmology, the situation is more subtle than that, because conservation laws depend on the structure of space-time you're working in. In ordinary situations, like mechanics, chemistry, engineering, or even most of special relativity, energy conservation works perfectly because the underlying space-time has a symmetry with respect to time. In a flat space-time like the Minkowski space-time used in special relativity, the laws of physics don't change over time, and according to Noether's theorem, that symmetry gives rise to conservation of energy. So in those systems, energy conservation is rock solid and extraordinarily useful. But the universe as a whole does not necessarily behave like flat space-time. In cosmology, we usually describe the large-scale structure of the universe using the Friedmann-Robertson-Walker metric, where space-time itself expands over time. And once space-time becomes dynamic like that, global energy conservation stops being straightforward. A classic example is light traveling across the expanding universe. As space expands, the wavelength of photons stretches, causing cosmological redshift, meaning the photons lose energy over time. And the uncomfortable question becomes, where did that energy go? The answer is basically that there is no globally conserved energy quantity in that spacetime the way there is in simpler systems. The universe doesn't store the lost energy somewhere else. The concept itself breaks down at cosmological scales because the symmetry required for strict conservation no longer exists, which is honestly one of the most counterintuitive things in modern physics, because it means one of the first absolute laws people learn turns out to depend on the geometry of the universe itself. Story 13. The weirdest thing about the quantum world is that certain properties aren't allowed to vary continuously the way our intuition expects, and instead can only exist in discrete chunks, which is what physicists mean when they say something is quantized. A really interesting example of this is angular momentum, which is basically the quantity that describes how much rotational motion something has. In ordinary life, angular momentum shows up everywhere: spinning wheels, planets orbiting stars, figure skaters pulling in their arms to spin faster. And it depends on things like mass, distance from the center of rotation, and rotational speed. At human scales, angular momentum feels completely continuous. A wheel can spin a little faster or a little slower by arbitrary amounts, and nothing seems chunked. But once you get down to the quantum level, nature suddenly stops allowing arbitrary values in many situations. Instead, angular momentum comes in discrete units. For systems like electrons and atoms, the allowed angular momentum values are integer or half-integer multiples of a fundamental quantity tied to the reduced Planck constant, often written as h bar, which is roughly 10 at minus 34 joule seconds. That number is absurdly tiny, which is why quantization doesn't show up in everyday rotating objects. The steps are so unimaginably small at macroscopic scales that everything appears smooth and continuous to us. But at atomic scales, those steps matter enormously. Electrons orbiting atoms can't just take any rotational state they want. They're restricted to specific allowed configurations, and that quantization is one of the reasons atoms are stable at all. So one of the strangest truths in physics is that rotation itself, something that feels completely fluid and continuous in daily life, becomes fundamentally pixelated at the smallest scales of reality. Story 14. A thing a lot of people outside physics don't realize is that the public image of physics is wildly skewed toward whatever sounds the most dramatic. Black holes, quantum weirdness, particle colliders, the origins of the universe, because those topics make great headlines and documentaries. But that's actually not where most physics research is happening day to day. A huge amount of modern physics is in condensed matter physics, which sounds boring compared to cosmology until you realize it includes semiconductors, superconductors, magnetism, quantum materials, nanotechnology, and basically a massive portion of the technology modern civilization runs on. And one of the really major areas is thin film research, where people study materials only a few atoms or nanometers thick. That's the kind of work tied to better batteries, solar panels, processors, displays, sensors, memory devices, and all sorts of advanced electronics. It doesn't get flashy headlines because slightly improved electron transport properties in layered oxide heterostructures doesn't sound as exciting to the average person as scientists discovered a weird black hole, even if the former may end up affecting billions of people technologically. A lot of the reason particle physics and relativity dominate pop science is because they involve giant collaborations, massive facilities, and huge funding pools. Things like the CERN naturally attract media attention because the scale is enormous and the concepts feel philosophical and cosmic. Meanwhile, condensed matter research is spread across countless smaller labs working on very specific material problems, often with smaller budgets and less public visibility, even though collectively it represents an enormous portion of actual physics output. So there's this weird disconnect where the physics most people hear about is often not the physics most physicists are actually spending their time doing. Story 15. Honestly, Newton's laws of motion might be the most important physics ideas the average person can actually understand intuitively, because once they click in your head, suddenly huge parts of the physical world start making sense in a way they didn't before. And the funny thing is, they're not actually that complicated conceptually. They just get taught in this dry, equation-heavy way that makes people think they're harder than they are. Newton's first law is basically that things keep doing what they're already doing unless something interferes. If an object is sitting still, it stays still. If it's moving, it keeps moving in a straight line unless a force acts on it. The reason objects seem to naturally stop in everyday life is mostly because friction and air resistance are constantly interfering. But remove those, and motion just keeps going. The second law is the famous force relationship, where more force means more acceleration, while more mass means harder acceleration. It's why kicking a soccer ball and kicking a car produce very different outcomes even if you use the same effort. And the third law, which people usually underestimate, is that forces always come in pairs. Push on a wall, and the wall pushes back on you. Rockets work because exhaust gases are blasted downward, and the rocket gets pushed upward in response. What's really cool now is that modern games and simulations accidentally teach people these ideas visually. Games like Angry Birds Space actually give surprisingly intuitive demonstrations of gravity wells, momentum, and orbital motion, because the software is simulating simplified versions of real physical laws. So, physics stops feeling like abstract equations and starts feeling like the hidden operating system underneath reality itself. Story 16. The strangest thing about light is that the light travels in straight lines. Idea is only an approximation that works at everyday scales, not the deeper reality of what's actually happening. In normal life, light behaves as if it moves straight, because the overwhelmingly dominant paths average out that way, so shadows, lasers, and vision all reinforce that intuition. But in quantum electrodynamics, especially as explained by Richard Feynman, the picture becomes much weirder. According to the quantum description, light doesn't simply pick one clean route from point A to point B. Instead, photons effectively explore every possible path between those points, including paths that look completely absurd from a classical perspective. Curves, loops, detours, wildly indirect routes, all of them contribute mathematically to the final result. Now, obviously we don't see light bouncing around chaotically everywhere, because most of those paths cancel each other out through interference. The paths near the classical straight-line route reinforce one another, while the bizarre routes mostly destructively interfere and disappear from the observable outcome. So at large scales, the surviving result looks like a straight beam of light, even though the underlying quantum behavior is far stranger. And this is one of those ideas that sounds philosophical or mystical until you realize it's not speculation, it's literally the framework that produces some of the most accurate predictions in all of science. Quantum electrodynamics matches experiments to an absurd degree of precision, which means that underneath the clean, intuitive world we experience every day, reality is operating according to rules that are much less straightforward than our brains evolved to expect. Story 17. The funniest thing about physics is how often incredibly complicated-looking problems secretly reduce to just triangles. People imagine physics as this terrifying wall of calculus and abstract equations. And sure, at advanced levels, it absolutely can become that. But an enormous amount of practical physics really comes down to understanding how vectors and angles work, which means basic trigonometry ends up being unbelievably useful. The reason is that nature rarely lines things up in perfect straight directions for us. Forces act at angles, motion happens diagonally, gravity interacts with slopes, waves spread in different directions, and once something isn't perfectly horizontal or vertical anymore, triangles immediately show up. A classic example is something sliding down a ramp. Gravity pulls straight downward, but the object doesn't move straight downward because the surface redirects the motion. So what physicists do is break the gravitational force into components using trig, one part perpendicular to the slope and one part parallel to it. Suddenly, a messy-looking problem becomes manageable just by using sine and cosine. The same thing happens everywhere else, too. Projectile motion, electricity, orbits, optics, engineering, even game physics all constantly rely on resolving things into triangle relationships. And what's interesting is that trig isn't really about triangles specifically at that point. It becomes a language for describing relationships between directions and magnitudes in space. So, a lot of physics stops feeling impossible once you realize you're often just translating the universe into simpler geometric pieces. Which is why understanding basic triangles ends up giving you way more access to the physical world than people usually expect. Story 18. What makes that quote from Richard Feynman so fascinating is that at first it almost sounds too simple. Like, surely all of science couldn't possibly be compressed into one statement about atoms moving around. But the more you think about it, the more you realize he wasn't exaggerating nearly as much as it seems. Because hidden inside that one idea is the foundation for an absurd amount of physics, chemistry, biology, and even geology. If matter is made of tiny moving particles, then temperature suddenly becomes understandable as motion. Heat isn't some invisible substance, it's atoms and molecules jiggling faster. Pressure becomes particles colliding with surfaces. Sound becomes vibrations propagating through matter. Chemistry becomes atoms rearranging into different structures because of electromagnetic attraction and repulsion. Even things that feel solid and static stop being what they appear to be. A table feels rigid, not because the atoms are literally touching in the intuitive sense, but because electromagnetic forces resist compression. Most of ordinary matter is actually empty space at atomic scales, which is one of those facts people hear but never emotionally process, because our brains evolved for the macroscopic world. And then once you follow the idea further, biology itself becomes chemistry, organized into self-replicating systems, stars become giant nuclear interactions between particles, and entire planets become collections of atoms obeying the same physical laws as everything else. That's what Feynman was getting at. Not that one sentence magically teaches all of science, but that if you truly internalize the atomic picture of reality, an enormous amount of the universe suddenly becomes explainable through interactions between tiny moving particles following consistent rules, which is honestly one of the most profound shifts in perspective science ever gave humanity, because it means the staggering complexity of the world emerges from relatively simple underlying principles interacting at massive scales. Story 19. The coolest thing in physics is that time travel to the future is not science fiction at all. It's a real consequence of relativity, and we've experimentally confirmed it many times. The key idea is that time does not pass at the same rate for everyone. The faster you move relative to something else, or the stronger the gravity around you, the slower your time passes compared to observers elsewhere. This effect is called time dilation, and while it's tiny at everyday speeds, it becomes dramatic as you approach the speed of light. So if someone traveled through space at extremely high speed for what felt like a few years to them, decades or even centuries could pass back on Earth. From the traveler's perspective, they effectively jumped into the future. And this isn't hypothetical in the sense of, maybe someday physics will prove it. We already measure time dilation constantly. Atomic clocks on satellites tick slightly differently than clocks on Earth because of both their speed and weaker gravity. And systems like GPS literally have to correct for relativistic effects or they'd stop functioning accurately very quickly. What we don't have is any experimentally verified way to travel backward in time. General relativity mathematically allows for some bizarre possibilities, like closed time-like curves or wormholes under very specific conditions. But those ideas require exotic circumstances and run into enormous physical and logical problems. So as far as actual demonstrated physics goes, the universe seems perfectly okay with one-way time travel into the future. It's the past that appears to be heavily protected. Story 20. Honestly, electromagnetism is probably the most underrated concept in physics for the average person. Because once you realize how much of reality is basically electromagnetism doing different tricks, the world starts looking completely different. People tend to think electricity, magnetism, light, chemistry, touch, electronics, and atoms are all separate topics, when in reality huge portions of them are manifestations of the same underlying force. Light itself is electromagnetic radiation. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, they're all the exact same phenomenon, just at different wavelengths and energies. Your phone, Wi-Fi, Bluetooth, sunlight, and MRI machines are all operating somewhere on the same electromagnetic spectrum. Even the feeling of solid objects touching is kind of misleading. When you press your hand against a table, the atoms are not truly colliding the way billiard balls do. What you're actually feeling is electromagnetic repulsion between the electron clouds of the atoms in your skin and the atoms in the table. So the sensation of solidity itself is largely electromagnetic interaction. Chemistry is electromagnetism too. Atoms bond because of electromagnetic attraction between electrons and nuclei. Biology depends on chemistry, which means, in a very real sense, a huge amount of life is electromagnetism organized into incredibly complicated patterns. And magnetism itself turns out to be tied to relativity in this weird, elegant way. A magnetic field can actually be understood as a relativistic effect of electric fields when charges are moving relative to an observer. So what initially seems like a bunch of disconnected physical phenomena ends up collapsing into one unified framework. And once you understand that, you realize electromagnetism is not just electricity and magnets, it's one of the main reasons ordinary matter behaves like a structured, stable world at all. Story 21. Bernoulli's principle is one of those physics ideas that seems weird at first because it feels backwards intuitively. Most people assume faster moving air should push harder, but in many fluid systems, faster-moving fluid actually corresponds to lower pressure. The classic example is an airplane wing. A wing is shaped so air moving over the top generally travels faster than the air moving underneath, and according to Bernoulli's principle, faster airflow above the wing corresponds to lower pressure compared to the higher pressure air below it. That pressure difference contributes to lift, helping keep the aircraft airborne. What's interesting is that people often oversimplify this into the air on top has to travel farther in the same amount of time, which isn't really the correct explanation. In reality, lift comes from a combination of pressure differences, airflow curvature, momentum transfer, and the wing deflecting air downward. Bernoulli's principle is a major part of the story, but not the only part. And once you understand the principle, you start seeing it everywhere. It explains why shower curtains get pulled inward when water runs, why roofs can lift off during strong winds, why blowing across the top of a piece of paper makes it rise, and even part of how carburetors and perfume atomizers work. The deeper realization is that fluids are constantly trading off between pressure, speed, and energy, and changes in one affect the others in ways that aren't always intuitive. So something as massive as a jetliner staying in the air ultimately depends on subtle pressure differences created by moving air, which is honestly kind of incredible when you stop and think about it. Story 22. The triple point is one of those physics concepts that sounds completely impossible until you actually see it demonstrated, because it means there's a precise combination of temperature and pressure where a substance can exist as a solid, liquid, and gas simultaneously, not switching rapidly between them, not partly one and partly another in separate regions. All three phases coexist in equilibrium at the same time. For water, this happens at a very specific pressure and temperature, and if you place water in a controlled vacuum chamber and carefully lower the pressure, you can literally watch liquid water begin boiling while ice crystals form at the same time. Which feels absurd at first because boiling and freezing seem like opposite processes. But the key is that phase changes don't depend only on temperature, they also depend heavily on pressure. Lowering the pressure reduces the boiling point of water dramatically, which is why water can boil at room temperature in a vacuum. At the same time, evaporation removes energy from the remaining liquid, cooling it enough for ice to form. So under the right conditions, all three states become stable together. And what's fascinating is that this isn't just a weird lab trick, it's a direct consequence of how matter organizes itself energetically. Every substance has its own phase diagram showing which state is favored under different conditions of temperature and pressure, and the triple point is the exact intersection where the boundaries between all three phases meet. It's one of those moments where physics stops feeling like equations and starts feeling genuinely alien, because watching something boil and freeze simultaneously forces you to realize that our everyday intuition about matter is really just based on the narrow range of conditions humans normally experience. Story 23. The Brazil nut effect is one of those deceptively simple physics problems that looks almost trivial until you realize scientists and engineers still actively study it because granular materials behave in ways that are surprisingly difficult to model. Most people have seen it happen without thinking much about it. You open a can of mixed nuts, shake it around a bit, and somehow the biggest nuts end up near the top instead of sinking downward like your intuition might expect. The same thing happens in cereal boxes, trail mix, containers of pills, industrial powders, and basically any mixture of particles with different sizes. At first glance, it feels like it should violate common sense because we're used to heavier things sinking in liquids. But granular materials aren't liquids in the normal sense. A pile of grains, nuts, or sand behaves somewhere between a solid and a fluid, and once you start shaking it, complicated collective motion emerges. One of the main explanations involves smaller particles slipping downward through tiny gaps that open beneath larger particles during shaking. Over time, the smaller particles effectively percolate downward, which pushes the larger particles upward relative to the mixture. There are also convection-like flows inside the material itself, where grains circulate in looping patterns somewhat similar to fluid convection. What makes this fascinating is that even though the effect is easy to observe, predicting granular behavior mathematically is incredibly hard, because you're dealing with huge numbers of interacting particles, friction, collisions, and changing force networks all at once. And this isn't just a quirky nut problem either. Industries transporting food, pharmaceuticals, mining materials, or powders constantly have to account for these effects, because segregation during transport can completely alter product consistency. So something as mundane as shaking a container of nuts ends up exposing how complicated many-body physics becomes once large numbers of simple objects start interacting collectively. Story 24. The strangest consequence of general relativity is that time is not universal or constant, and it literally flows at different rates depending on gravity. The stronger the gravitational field you're in, the slower time passes relative to someone farther away from that gravity source. And this isn't philosophical or metaphorical, it's a physically measurable effect called gravitational time dilation, which means that someone living on the top floor of a skyscraper is actually aging very slightly faster than someone on the ground floor, because they are a tiny bit farther away from Earth's gravitational pull. The difference is absurdly small in everyday life, tiny fractions of a second over many years, so you'd never notice it biologically. But with precise enough atomic clocks, we can measure it directly. And what's wild is that modern technology actually depends on accounting for these differences. GPS satellites orbit far above Earth, where gravity is weaker, so their onboard clocks tick faster than clocks on the surface. If engineers ignored relativity, GPS positioning errors would accumulate extremely quickly, and the system would become useless. The deeper realization here is that gravity is not just a force pulling things downward in the Newtonian sense. In Einstein's picture, gravity changes the geometry of space-time itself, and time becomes part of the thing being warped. So the universe does not contain one master clock ticking the same everywhere. Time itself depends on where you are, how fast you're moving, and what gravitational environment you exist in. And once you really internalize that, the everyday idea of time as this universal background thing starts to completely fall apart. Story 25. One of the coolest little physics phenomena most people have never heard of is triboluminescence, because it sounds completely fake until you actually see it happen yourself. If you peel certain kinds of adhesive tape, like Scotch tape, in a dark room, you can sometimes see tiny flashes of blue light coming from where the tape separates from the roll. And under the right conditions, experiments have shown the process can even generate small amounts of X-rays, which is absolutely not something your brain expects ordinary office supplies to be capable of doing. What's happening is basically a violent separation of electrical charges. As the adhesive pulls apart, electrons get redistributed unevenly between the surfaces, creating regions of positive and negative charge. Eventually, the electric field becomes strong enough that electrons suddenly jump through the air or material, ionizing molecules and releasing energy in the form of light. It's somewhat related to static electricity, just on a much more localized and energetic scale. And the X-ray part sounds especially insane, but it comes from the same basic idea. Under vacuum conditions, the separated charges can accelerate electrons enough that when they suddenly decelerate after collision, they produce X-rays through a process similar to what happens in X-ray tubes, which means peeling tape can technically become a tiny particle accelerator. What makes triboluminescence fascinating is that it reveals how much electromagnetic activity is hidden inside ordinary materials and everyday interactions. Breaking crystals, crushing sugar, peeling tape, or separating surfaces can all create electric fields and light emissions we normally never think about. So something as mundane as pulling tape off a roll ends up exposing deep connections between electricity, atomic structure, radiation, and energy transfer in matter. Story 26. Sonoluminescence is one of those physics phenomena that sounds completely impossible the first time you hear about it, because the basic idea is literally that sound can create light, not metaphorically, actual flashes of light. What happens is that powerful sound waves traveling through a liquid can create tiny bubbles that rapidly expand and collapse in sync with the pressure changes of the sound field. Most of the time, bubbles are boring, but under very specific conditions, the collapse becomes incredibly violent. As the bubble implodes, the gas trapped inside gets compressed into an absurdly tiny volume in an extremely short amount of time, and that compression drives the temperature and pressure sky high. For a brief instant, the interior of the bubble can reach temperatures estimated above 10,000 Kelvin, potentially even much higher depending on the model, which is hotter than the surface of the sun. And during that collapse, a tiny pulse of light is emitted. What makes this phenomenon so fascinating is that scientists still debate the exact microscopic mechanism behind the light production itself. We understand the overall process reasonably well, but the detailed physics inside the collapsing bubble becomes extremely extreme very quickly, involving shock waves, plasma formation, ionization, and possibly quantum effects. So you end up with this bizarre situation where ordinary sound waves in water can create tiny regions of extreme conditions that briefly resemble astrophysical environments. And the scale contrast is what really messes with your intuition. You're not talking about giant explosions or particle accelerators. You're talking about microscopic bubbles in liquid being driven by sound vibrations, somehow concentrating enough energy during collapse to momentarily produce temperatures rivaling stars. Story 27. The most visually beautiful thing in physics is Cherenkov radiation, which produces that eerie blue glow you sometimes see in nuclear reactors. And the reason it happens sounds like it should violate physics, until you understand the very important detail that nothing is actually exceeding the speed of light in a vacuum. People often hear faster than light and immediately think relativity has been broken, but light only travels at its absolute maximum speed in empty space. When light moves through a material like water or glass, it slows down because it constantly interacts with the atoms in the medium. Charged particles, however, can sometimes move through that same medium faster than light can move through the medium itself, even though they're still traveling slower than light's ultimate vacuum speed limit. And when that happens, you get something very similar to a sonic boom. A jet moving faster than sound creates a shock wave because it outruns the pressure waves in the air. In the same way, a charged particle outrunning light in water creates a kind of electromagnetic shock wave, emitting a cone of blue light known as Cherenkov radiation. That glowing blue effect in reactor pools is basically a photonic sonic boom, and the color itself comes from the fact that shorter wavelengths, especially blue and ultraviolet light, are emitted more strongly in the process. What makes it so fascinating is how alien it feels intuitively. Water, something calm and familiar, can suddenly become the stage for relativistic particles generating visible shockwaves through space-time and electromagnetism. So that haunting blue glow isn't just radiation in the vague, scary sense people imagine. It's visible evidence of particles moving at relativistic speeds and literally outrunning light's local speed through the medium around them. Story 28. The Mpemba effect is one of those physics problems that sounds so obviously wrong that people assume it must be a myth, because intuitively it feels impossible that hot water could ever reach freezing before colder water does. After all, the hot water has farther to go. It should have to cool down to the colder water's temperature first, and then continue freezing, so common sense says the colder sample should always win. But under certain conditions, experiments really have shown hot water freezing faster, or at least beginning the freezing process sooner, and the phenomenon has been reported for centuries. What makes it especially interesting is that there still isn't one universally accepted explanation that accounts for every case consistently. Instead, physicists think multiple effects may contribute depending on the setup. Hot water evaporates more, which reduces the amount of water that actually has to freeze. Heating can also change dissolved gases in the water, alter convection currents, or affect how ice crystals initially nucleate. In some situations, the warmer container may establish stronger circulation patterns that distribute heat differently, allowing cooling to proceed more efficiently. There are even cases where frost buildup or thermal contact with the environment changes differently between the hot and cold samples. So the Mpemba effect may not be one single mechanism so much as a collection of overlapping processes that can occasionally combine in ways that let hot water freeze faster than colder water. And that's what makes it such a fascinating physics problem. Not because it breaks thermodynamics, it doesn't, but because it reveals how messy real-world systems become once you include evaporation, fluid dynamics, dissolved gases, convection, and phase transitions all interacting at once. It's a reminder that even something as apparently simple as freezing water can become surprisingly complicated once you look closely enough. Story 29. A perfect vacuum, what we casually think of as empty space, is not actually empty at all. In classical physics, a vacuum was imagined as true nothingness, just blank space with absolutely no matter or activity inside it. But in quantum field theory, empty space turns out to be more like a restless background full of fluctuating fields that can never become perfectly still. What people often call virtual particles are part of this picture. Due to the uncertainty principle, quantum fields can briefly fluctuate, creating temporary particle-antiparticle pairs that appear and disappear on incredibly tiny timescales. Now, it's important to note that virtual particles are not little ordinary particles literally popping into existence, like tiny sci-fi sparks in space, the way pop science sometimes portrays them. They're mathematical features of quantum field interactions. But the effects associated with these fluctuations are very real and experimentally measurable. For example, phenomena like the Casimir effect, where two extremely close metal plates experience a tiny force due to quantum vacuum fluctuations, strongly suggest that even empty space possesses physical structure and energy. And this completely changes the philosophical meaning of nothingness. In quantum physics, the vacuum is not a passive emptiness. It's the lowest energy state of interacting quantum fields, and those fields are always fluctuating slightly because the laws of quantum mechanics prevent them from being perfectly motionless. So the universe at its deepest level looks less like matter sitting inside empty space, and more like fields existing everywhere continuously, with particles emerging as excitations of those fields, which means that even the closest thing physics has to nothing still turns out to be an active, dynamic something. Story 30. The most mind-bending idea in theoretical physics is the holographic principle, because it suggests that the three-dimensional universe we experience might, at a deeper level, be describable by information encoded on a lower dimensional surface. And the weird part is that this isn't just random philosophy or simulation theory internet speculation. The idea emerged from very serious attempts to understand black holes and quantum gravity. The problem started when physicists realized black holes appear to store information in a way that scales with their surface area, not their volume. That's deeply counterintuitive because we normally expect information capacity to grow with volume, like how a bigger hard drive stores more data internally. But calculations involving black hole thermodynamics suggested that the maximum information inside a region of space might actually be proportional to the area surrounding it. From there came the idea that maybe our usual picture of reality is redundant somehow, and that the physics happening inside a region could potentially be fully described by information encoded on its boundary, almost like a hologram generating a three-dimensional image from a two-dimensional surface. A major realization supporting this came from something called the ADS/CFT correspondence, where, in certain mathematical models, a gravitational universe in higher dimensions turns out to be equivalent to a quantum field theory existing on a lower dimensional boundary, without gravity. Now, this does not mean physicists think the universe is literally fake, flat, or secretly a computer screen. The analogy to a hologram is about information encoding and mathematical equivalence, not about us being illusions. And importantly, we do not know whether the holographic principle applies exactly to our own universe in a complete sense. But what makes it so fascinating is that it hints at space-time itself. The thing we intuitively think of as the stage of reality might actually emerge from something deeper and more fundamental underneath. Story 31. The Leidenfrost effect is one of those everyday physics effects people have probably seen dozens of times without realizing how strange it actually is. If you sprinkle water onto a moderately hot pan, the droplets just sizzle and evaporate quickly like you'd expect. But if the pan gets extremely hot, suddenly the droplets start gliding around almost like little hovering UFOs, skittering across the surface and surviving much longer than they should. And weirdly enough, the hotter surface can actually make the water evaporate more slowly for a while. What's happening is that the bottom layer of the droplet vaporizes so rapidly upon contact that it creates a thin cushion of steam underneath the liquid. That vapor layer acts as an insulator, preventing most of the remaining water from directly touching the pan. So instead of sitting against the metal and boiling violently, the droplet is effectively levitating on its own vapor. Because the friction becomes extremely low, tiny asymmetries in the escaping steam can propel the droplet around the surface, giving it that dancing motion. And this isn't just a kitchen curiosity either. The effect matters in industrial cooling, metallurgy, nuclear reactor safety, and heat transfer engineering, because vapor layers can dramatically change how efficiently heat moves between surfaces and liquids. It also creates some wonderfully counterintuitive demonstrations, like briefly dipping a wet finger into molten lead or liquid nitrogen interactions, where the vapor layer provides temporary insulation, though obviously that's not something people should casually try. So what looks like simple dancing water is actually a surprisingly sophisticated interplay between phase transitions, insulation, fluid dynamics, and heat transfer all happening at once. Story 32. Quantum tunneling is one of those things that sounds like pure science fiction until you realize modern civilization literally depends on it working. In classical physics, if a ball doesn't have enough energy to get over a hill, it simply cannot cross to the other side. End of story. But quantum mechanics does not treat particles as tiny billiard balls with perfectly defined positions and paths. Instead, particles are described by wave functions, which spread out probabilistically through space. And because of that wave-like nature, there's always some chance that part of the particle's wave function extends through a barrier, even one the particle classically shouldn't have enough energy to cross. Under the right conditions, the particle can effectively appear on the other side as though it tunneled through the obstacle. Not because it smashed through it, not because the laws broke, but because quantum mechanics fundamentally does not operate according to classical trajectories at microscopic scales. What's incredible is how important this effect becomes in reality. Inside the Sun, positively charged atomic nuclei should repel each other too strongly to fuse at the temperatures present there. Classically, fusion would happen far too rarely for the Sun to shine the way it does. But quantum tunneling allows some nuclei to penetrate the energy barrier and fuse anyway, which is ultimately why stars produce energy and why sunlight exists at all. And on Earth, tunneling is essential for technologies like flash memory, scanning tunneling microscopes, semiconductor devices, and many electronic components. So one of the deepest truths about the universe is that at very small scales, particles are not strictly confined by the intuitive "you can't pass through walls" logic our brains evolved to expect. Reality at the quantum level is fundamentally probabilistic, and sometimes nature allows things to cross barriers that classical physics says should be impossible. Story 33. The Casimir effect is one of those experiments that feels almost unsettling the first time you understand what it's implying, because it means that completely empty space can produce a measurable physical force. The setup sounds absurdly simple. Take two uncharged metal plates, place them extremely close together in a vacuum, and they will slowly move toward each other even though there's no conventional force pulling them together. No magnetism, no static electricity, no obvious interaction. And yet the force is real and experimentally measurable. The usual simplified explanation involves so-called virtual particles and quantum vacuum fluctuations. In quantum field theory, empty space is not truly empty, but filled with constantly fluctuating fields. Between the plates, only certain wavelengths of these fluctuations are allowed to exist because the boundaries restrict the possible electromagnetic modes. Outside the plates, however, there are more allowed fluctuations. So you end up with slightly more vacuum pressure pushing on the outside than on the inside, which creates a net force pushing the plates together. Now, the virtual particles popping in and out of existence explanation is a somewhat simplified pop science language for what's mathematically happening, but the underlying effect itself is absolutely real. And what makes it so profound is that it demonstrates the vacuum has physical structure. Empty space is not just passive nothingness. The quantum vacuum has measurable consequences that can affect matter directly. The force is tiny unless the plates are incredibly close together, so it's not something you notice in daily life. But at microscopic scales, it becomes important in nanotechnology and micro-electromechanical systems because these tiny forces can influence moving parts. So the Casimir effect ends up being one of the clearest demonstrations that, in modern physics, nothing is not actually nothing at all. Story 34. The most bizarre thing in quantum physics is that some particles literally do not return to the same quantum state after a normal 360-degree rotation. For particles like electrons, which are examples of spin 1-2 particles, you actually need a full 720-degree rotation, 2 complete turns, before the system fully comes back to its original configuration. And this is not just a weird metaphor or mathematical trick. It's built directly into the structure of quantum mechanics. Now, spin itself is already misleading terminology, because the particle is not literally spinning like a tiny ball. Electrons are effectively point-like in our current understanding, so there's no little surface physically rotating around an axis. Spin is instead an intrinsic quantum property related to angular momentum and how the particle behaves under rotations. What makes spin 1-2 particles so strange is that if you rotate 1 by 360 degrees, the mathematical description of its quantum state changes sign. Physically measurable quantities remain the same, which is why we don't notice anything weird in ordinary observations, but at the wave function level, it is not fully identical yet. Only after another full 360-degree turn totaling 720 degrees does the quantum state completely return to its original form. And amazingly, this weirdness is not just abstract mathematics either. It produces real measurable consequences in experiments involving interference and quantum phase relationships. There are even famous demonstrations using belts, plates, or arm-twisting tricks that mimic the topology behind this behavior, where you can untangle a system after 2 rotations but not 1. So one of the deepest lessons from quantum mechanics is that particles do not obey our everyday geometric intuition. At the microscopic level, even something as seemingly simple as rotating an object in a circle stops behaving the way common sense says it should. Story 35. Bose-Einstein condensate is one of the closest things physics has to making matter behave like a single giant quantum object. And the fact that it can exist at all is honestly kind of unbelievable. Normally, atoms behave like distinct individual particles bouncing around randomly because temperature corresponds to motion. The hotter something is, the more energetic and chaotic the atomic motion becomes. But when you cool certain atoms to temperatures, only tiny fractions of a degree above absolute zero, that motion drops so dramatically that something very strange starts happening. The atom's quantum wave functions begin spreading out enough to overlap with each other. And once that overlap becomes large enough, the atoms stop behaving like clearly separate individuals and instead collapse into the same collective quantum state. At that point, the entire group effectively acts like one enormous superatom with a shared wave function, which means quantum mechanics, something normally hidden deep in microscopic scales, suddenly becomes visible at macroscopic scales. Instead of quantum behavior averaging away into ordinary classical physics, it starts dominating the entire system. You can get bizarre effects like superfluidity, where the condensate flows with essentially zero viscosity, climbing container walls, or circulating endlessly without friction, under the right conditions. What makes this especially profound is that it reveals the boundary between the quantum world and the everyday world is not fixed. Classical reality is not some separate layer of physics, it's what usually emerges when huge numbers of quantum systems become noisy and thermally chaotic. But near absolute zero, that noise disappears enough for quantum behavior to organize coherently across an entire visible collection of atoms. So Bose-Einstein condensates are basically a glimpse into what reality looks like when matter stops behaving like separate particles and starts behaving like one unified quantum entity. Story 36. The observer effect is one of those ideas that gets wildly distorted in pop culture, because real physics is already strange enough on its own. So people start attaching all kinds of mystical interpretations to it that quantum mechanics does not actually require. What's genuinely true is that in quantum systems, measurement is not a passive process. At microscopic scales, particles are described by wave functions representing probabilities rather than definite classical states, meaning properties like position or momentum do not behave as fully determined values in the way everyday objects do. And in certain experiments, especially things like the famous double-slit experiment, the behavior changes dramatically depending on whether information about the particle's path is measured. Without path measurement, particles produce interference patterns consistent with wave-like behavior, as though the particle explored multiple possible paths simultaneously. But once a measurement determines which path the particle took, the interference disappears and the system behaves more classically. That's the genuinely weird part. Not that human consciousness magically creates reality, but that interactions which extract information from the system fundamentally alter what outcomes are possible. And importantly, observation in physics does not mean a conscious mind watching something. A detector, photon interaction, sensor, or any physical interaction capable of recording information counts as a measurement. The universe does not appear to wait for a human to look at it before deciding what to do. What's still debated is how to interpret all this. Different interpretations of quantum mechanics disagree on what the wave function really represents, and whether collapse is a physical process, an informational update, or something else entirely. But regardless of interpretation, the experimental results are undeniable. Quantum systems behave differently when measurable information about them becomes available, which means reality at microscopic scales is not built like the deterministic clockwork universe people once imagined, and the act of measurement itself becomes part of the physics instead of something external to it. Story 37. Gravitational lensing is one of those physics effects that sounds almost magical when you first hear about it, because it means gravity can literally bend light and turn entire galaxies into gigantic natural telescopes. In everyday life, we think of gravity as simply pulling objects together, apples falling, planets orbiting, things having weight. But according to general relativity, gravity is actually the result of mass warping space-time itself. And since light travels through space-time, its path gets bent when it passes near something extremely massive. So, if a distant galaxy or star lies behind another massive object, from our point of view, the foreground object can distort and magnify the light coming from behind it, acting somewhat like a giant cosmic lens. Sometimes this creates stretched arcs of light, duplicated images, or even complete glowing rings called Einstein rings, where the alignment becomes almost perfect. And this isn't just visually beautiful, it's incredibly useful scientifically. Astronomers use gravitational lensing to detect extremely distant galaxies that would otherwise be far too faint to observe directly. In some cases, lensing magnifies ancient light from the early universe that has traveled billions of years to reach us. It's also one of the strongest tools we have for studying dark matter, because we can map invisible mass distributions by observing how they bend background light. What makes gravitational lensing so profound is that it's a direct visual demonstration that space itself is not a rigid, empty stage. Massive objects actually reshape the geometry of the universe around them, and light simply follows those curves. So when astronomers observe distorted galaxies across the cosmos, they are literally watching space-time bend in real time on an intergalactic scale. Story 38. The most embarrassing and genuinely unsettling problems in modern physics is the cosmological constant problem, sometimes jokingly called the vacuum catastrophe, because it represents what may be the single worst theoretical prediction ever produced in science. In quantum field theory, empty space is not actually empty. Quantum fields fluctuate constantly, and those fluctuations contribute a background energy to the vacuum itself, often called vacuum energy. The problem is that when physicists calculate how much vacuum energy quantum mechanics says should exist, the answer comes out absurdly enormous. Meanwhile, when astronomers observe the actual expansion of the universe, especially through effects associated with dark energy, the amount of vacuum energy implied by reality is tiny by comparison. And not just a little off. The mismatch is on the order of 10 to the 120th. That is a 1 followed by 120 zeros. To put that into perspective, physics usually celebrates theories that match experiments to maybe 10 decimal places. Being off by 120 orders of magnitude is so catastrophically wrong that it almost feels like nature is mocking us. And what makes this especially disturbing is that both sides of the problem individually work extremely well. Quantum field theory is one of the most experimentally successful frameworks ever created. Cosmological observations also consistently support the observed expansion behavior of the universe. But when you try to combine them naively, the numbers explode into nonsense. So somewhere, something fundamental about our understanding is incomplete. Maybe we're misunderstanding vacuum energy. Maybe gravity behaves differently at quantum scales. Maybe unknown cancellation mechanisms exist. Maybe our framework itself breaks down. Nobody really knows, which is why many physicists consider this one of the biggest clues that our current theories, despite being extraordinarily successful in many situations, are still missing something deep about the structure of reality itself. Story 39. Time crystal is one of those concepts that initially sounded so bizarre that many physicists thought it had to be impossible because it seemed to imply a system could keep changing forever without consuming energy, which immediately raises alarm bells about the second law of thermodynamics and perpetual motion. The original idea came from asking a strange question. Ordinary crystals repeat patterns in space, atoms arranged in repeating structures across physical dimensions. So could there exist a system that repeats in time instead? At first, that sounded nonsensical, because systems in their lowest energy equilibrium state are not supposed to exhibit ongoing motion. If something keeps ticking, intuition says energy must be getting spent somewhere. But then physicists realized certain driven quantum systems could settle into stable repeating cycles that occur at regular intervals in time, effectively creating temporal patterns analogous to spatial crystal structures. What makes time crystals especially weird is that their oscillations can persist without heating up and randomizing the system the way ordinary driven matter normally would. In experiments using carefully controlled quantum systems like trapped ions or defects in diamond, the particles repeatedly flip states in synchronized patterns that remain remarkably stable. Now, despite pop science descriptions, time crystals do not actually violate thermodynamics or create free energy. they still require specific quantum conditions and external driving in most realizations. The key weirdness is not infinite energy, but that the system organizes into a persistent repeating structure in time while avoiding the normal thermal decay you'd expect. And philosophically, what makes them so fascinating is that they blur our intuition about phases of matter entirely. We normally think of matter phases as static spatial arrangements, solids, liquids, crystals, but time crystals reveal that under quantum mechanics, matter can also organize itself through repeating behavior across time itself, which is one of those ideas that sounds more like abstract science fiction than something experimentally demonstrated in actual laboratories. Story 40. The most deeply unsettling idea in modern physics is the Unruh effect, because it suggests that even something as fundamental as whether empty space contains particles depends on how you are moving. In ordinary intuition, a vacuum is either empty or it isn't. That seems like an objective fact about reality, but quantum field theory combined with relativity starts tearing apart that assumption in very strange ways. According to the Unruh effect, an observer sitting still in empty space would perceive a vacuum, basically nothing there except quantum fluctuations. But an observer accelerating through that exact same region of space would detect what appears to be a bath of warm particles surrounding them, almost like the vacuum itself had a temperature. So two observers can disagree about whether particles are present at all, even while looking at the same spacetime, and neither observer is considered wrong. The faster the acceleration, the hotter this apparent radiation becomes. At normal human accelerations, the effect would be absurdly tiny and practically impossible to notice, which is why we don't experience it in daily life. The temperatures involved only become significant under extreme accelerations far beyond ordinary circumstances. What makes this so profound is that it connects deeply to the structure of quantum fields and space-time itself. In quantum field theory, particles are not really tiny standalone objects in the classical sense. They are excitations of underlying fields, and different observers can decompose those fields differently depending on their motion. The Unruh effect is also closely tied mathematically to Hawking radiation, where black holes are predicted to emit thermal radiation because of quantum effects near the event horizon. So the terrifying implication here is that emptiness itself is not absolute. Even the vacuum depends on perspective, which means that at the deepest level, reality is much less objective and straightforward than the solid, observer-independent world our everyday intuition assumes exists.